Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about sparse representation of signals and images. In particular, we are considering only one-dimensional sequences, which means signals. And in the previous class, we have discussed several kind of matching pursuits algorithm. Given a dictionary, what could be the optimal representation of a vector using the elements of those dictionary. Today, we will consider the problem in a bit different way. Here, the dictionary itself needs to be learned. So, not only the optimal representation of the input data points, but also the dictionary. So, let us try to understand that what this problem is specified here, how this problem is defined. So, we have a set of data points, that is denoted by here xi. As you can see, it's a vector in an n-dimensional real space, and then these vectors to be represented by a dictionary of k atoms. So, which means there could be maximum k atoms whose linear combination will be approximately representing a vector xi. So, naturally atoms are also of the same dimension. That means atoms should be also in the same n-dimensional real space, and that is the problem. So, we need a dictionary which will give us the best possible sparse representation each member of the set, and also when we get the dictionary, we also get the representation. So, the motivation behind this problem is that we would like to have adaptive dictionaries for special classes of signals or data of interest. So, you have noticed here, instead of providing a particular vector whose optimal representation we want from a given dictionary of atoms, here we have provided a set of input vectors. So, the optimal representation is with respect to that set. So, that's why we are saying that specific classes of signals or data of interest. So, we are kind of taking different representative samples from those classes, and that from that input data set. So, from the learning perspective, we can consider these are the training data set from which dictionary is learned, and after the dictionary is being learned, then you consider any kind of arbitrary data point in that class and use that dictionary to represent it. So, since you are learning for a class, so this dictionary should be a good choice for representing those classes of signals or data of interest. So, it makes your computation application specific. Then also what you are doing while learning this dictionary, you are ensuring that sparse representation properties are also that should be ensured. So, let me state the precise problem statement what we have just qualitatively mentioned in the previous case. We will further quantify it in terms of defining the errors and representations. So, we consider a set of vectors that is, as I was saying, that these are the representative data vectors from the class, and this set is denoted here by x. So, this is the set, and you note that x1, x2, xn, these are vectors. Actually, these are all vectors, they are not scalar, which means they are all column vectors and of dimension n. So, the number of vectors is capital N. So you note this notations, which means this is my input data matrix, where each data point is a column vector of that data matrix. So this is how it is represented. Just to clarify further, if you say x1 is a column vector, so I can write it as say x11, x12 to say x1n. Similarly, you can write x2 in the same way you can write it. So if I expand this particular matrix representations with these respective elements of the column vector, we will write it in this fashion. You may note that in my notation, for my convenience, I am using the first suffix for the column notation and the second one for the row, notations. Just that is for the convenience, because I have started with 2. So this is representing a column. So I am using this kind of notations. I hope you will be able to understand this. So this is my data matrix. So this is given. Okay. And what other things are given? That now it is not given. Rather, I should say these are all representations. You have to compute it. So what you have to compute? You have to compute learn a dictionary of k atoms, which are also, you can see, that represented in the form of a matrix where each column is an atom. In the same way, this is of n dimension. So I can write also D in the same fashion, say D11, D12 to say D1n, and similarly dk1, dk2 to dkn. So there are k columns. There are k columns for which you have a column vectors, and since you are representing any vector as a linear combination of these atoms, so these atoms should be also of the same dimension of input data point, which is of n dimension, as you can see. But when we are considering the coefficients, so how now I can write as say x1, this vector can be written as say y11 d1 plus y12 d2 plus y1k dk. So this is a linear combination representation. Now this, so which means this representation it says that, so this y11, y12, y1k, these are the coefficients. So they are representing a column vector y1. So in the matrix form, I can consider the say respective data point, say for x1 vector, x11 to x1n. Then I am using the column vector d1, d2 to dk, and then it is basically multiplied by y11, y12 to y1k. So these are the coefficients. So this expression itself, as you have seen earlier also for matrix multiplications, so every column, it is transforming a column of k dimensional vector into an n dimensional vector using this dictionary. So this is the role of the dictionary. So this is an alternative representation, and we expect that this representation is sparse, which means there would be quite a few of zero elements or only a few non-zero elements out of these k elements. So that is the sparse representation that also we would like to achieve. So in our problem statement we would come to that point. So this is about your representation of the vector x1 in terms of the dictionary, and a particular coefficient vector y1, coefficient column vector. Similarly, so in the matrix, submatrix form I can write, so for x1 I am having a dictionary, so I am writing this thing as dictionary D, so D, and there I am having y1. Then for x2 again y2, so dy2 would be x2. So the matrix multiplication goes like this, and similarly if I have n such samples, that is my input data point. So for the nth sample also I have the nth column vector coefficients, and if I multiply it with the dictionary D, I will get the nth sample. So this represents this considers the final representation in this form, which we would like to get that, say, dictionary or set of atoms of the dictionary, k atoms, and also respective set of coefficients whose linear combination will give a close approximation of this x, or I can just say that now equal to dy, that is the thing we want. Exact reconstruction means that, but as you understand that exact reconstruction may not be always possible. So just to summarize once again this problem, I was mentioning that you have the input data vector x, you have the dictionary of k atoms D, you have the respective representation, sparse representation of each column vector of x by corresponding column vectors of y. So this should be considered to obtain a sparse representation y in a k-dimensional real space. Earlier it was n-dimensional, now it is k-dimensional, so that either it is exact or it is approximate representation. So this is your problem statement. So this becomes actually, so let us once again revisit the respective dimensions of each element here. As you can see that x is a input data point of dimension small n cross capital N, because the number of rows will be small n, that is the dimension of each data point, and number of columns will be the number of data points, which is capital N. Similarly, for the dictionary D, again dimension of each atom is also small n, because its linear combination should give you one of these data point, and then number of atoms are k atoms, so that is why this is k. So number of columns would be k. And for the coefficients, in this case, as you can see that in the linear expansions you require only k coefficients of k atoms. So that is why the dimension of each coefficient column vector should be k, and for each data point you have this representation, so there should be n such representation, so you have n column data point. So that is how the dimension is mentioned. And we can now you can also apply certain sparsity constraints. Now here we have not mentioned anything about sparsity of representations of the column vector of y. So now we can put also sparsity constraints on the column vectors of y. So we can say that minimum of, this is called norm 0, which means number of non-zero elements in y. So which means if I consider the total, say, matrix y, then what is the number of non-zero elements? That could be 1. So we would like to have that kind of representation where this is minimum subject to x equals dy. Now this is a hard satisfaction constraint, but you can give a tolerance that if the deviation is less than bound, the error is bounded by epsilon. This is a norm 2 specification as we discussed in the previous lecture. So there is an algorithm which is very effective and which is widely used for this purpose. This algorithm is called K singular value decomposition or K SVD algorithm. So this algorithm tries to solve this problem. So it forms both dictionary and sparse representations in a near optimal manner. So here once again the same problem as I have mentioned, but that it just says that given a set of training signals, you have to obtain a dictionary of k elements that leads to the best possible representations for each member in the set with strict sparsity constraints. That means, so there are again two variations you can see, and this is a reference which I have also mentioned here. So you can read this paper, one of the very significant contributions in this field particularly. So what are the flavors of this k singular value decomposition algorithms? In one way, you can consider as if it's a generalization of k-means clustering algorithm. Of course, it is much different than k-means clustering, but I am saying task-wise or result-wise, it's a kind of generalization. Because what you do in k-means clustering problem, you find out the cluster representatives, k cluster representatives, then the members of the clusters, they could be considered as represented by their means only. So it's very sparse representation, but of course it will give you large approximation errors. Only one of the atoms is used. So means of the cluster, that k means, they are the atoms of the dictionary, and each data point is represented by one of them, depending upon in which cluster the data point lies. So that is how it is a kind of the sparse representation. So in KSVT algorithm, rather we are not considering only belongingness to only one cluster, it's a linear combination of one means. So in k-means clustering, we have extreme sparse representation of a signal by a single atom only. So that is the case. Whereas in k singular value decomposition, a sparse linear combination of k atoms are obtained. So just to give you that once again, just recapitulate, I have discussed earlier also k-means clustering problem, or the algorithms to solve it. One of these algorithms which is Lloyd's algorithms, which are simple to implement and to understand also. So here we choose a dictionary of k atoms, then you obtain sparse representation as I mentioned, and then update the dictionary atoms. So in the KSVT algorithm, it goes like this. So you can update dictionary atoms so that your representations becomes sparser. So you are from one representations you are going to sparser, but not only sparser, your representation should also satisfy the error bound. So both it should lead to the better representation, better approximation, and also what is the best sparsity at that point could be achieved. So it's a kind of greedy algorithm. Once again, they provides a near optimal solution. So just to I was mentioning to once again to describe the k-means clustering algorithm for the sake of continuity. So we consider a k-means clustering algorithm in this way, that you have a set of atoms and then you assign the training examples to their nearest neighbor in the dictionary. So you start with a set of atoms. You can initialize with any arbitrary set of atoms. Those are particularly as if the means of the clusters. And then you assign the training examples to their nearest neighbor in D, and given the assignment, update D to better fit the examples. So usually L2 norm is used for assigning the neighbors, and for updating, what you do, update the mean of each partition of assignment. And you can start with any initial set of distinct atoms. And then the convergence will be it will converge to finally to certain set of atoms or means, and that is your representatives, representatives of each clusters. And as I was saying, that you can represent using a extreme sparse representation, you can represent each sample. So here also so instead of dictionary, sometimes we use this term code book, because as if these are the codes. Atoms are considered codes, and their linear combination is given the respective samples. And these are the, say, training examples I mentioned. This is the input data point. So extreme sparse vector representation would look like this. There would be only one non-zero element, and that too, the value is 1 here, because you are choosing one of these atoms. So if I say in my previous notations, say your dictionary D1, D2 to dk, and then for the xjth sample vector, I am using 0, 0, say at some point 1, 0. So all are 0, only 1 is 1. Suppose this column is ith, this row is ith row, which means xj is represented by di. So that is the meaning of sparse representation or extreme sparse representation, using the results of k-means clustering, using the means as the atoms of a dictionary. Now for SBD algorithm, KSBD algorithm, this could be the starting point, and then you go on iterating to get better representation approximation wise, and as well as maintaining the sparsity of the data. Ensure trying to get as much as sparse it is possible. So that's what I explained. Only one term is 1, rest are 0. So in the sparse representation, you have is one of these EJs. So in the sparse representation. So your optimization problem of this case we will be considering as to minimize. So when you are not making exact representation, you have to obtain D and Y such that Y is sparse and also it minimizes this. So this is L2 norm, but for a matrix we denote it as a Frobenius norm. It is the same as only in a vector. Let me explain that also. So in a vector, say in a column vector, you have the component like this, x1, x2 to xn. So when I am saying L2 norm, as I have also earlier mentioned, it is basically sum of the square of every element and then take square root of it. Now suppose it is a matrix. Suppose it is a matrix of element A1, 1, 2, say A1m, and I am using row notation here. Let it be A21, say A2m, and say AN1 to ANn. Suppose this is a matrix. So Frobenius norm of this matrix can be represented as sum of square of all the elements. And then you take the square root of it. So that is the Frobenius norm. And here you are using square, means you are not using the square root, you are simply minimizing square of this norm itself, which means square root operation is avoided in my expression. But you have to apply the constraint. So yi equals er, if this is the k-means assignment it is explaining. So update the means for all j. So this is still explaining the k-means algorithm, but it is trying to solve this problem in this fashion, but with the constraint that the structure of y looks like this. That is the constraint. I just mentioned this is Frobenius norm. So now let us try to understand the generalization of this approach for k singular value decomposition approach. The term singular value decomposition, you know that it's a it's a very well-defined operations for any matrix. So, because K similar value decomposition requires a computation of similar value decomposition K times. For each atom, you are performing a similar value decomposition. But then again, you do it iteratively. So, it is a number of iterations that you do. For that, you require so many similar value decompositions. So, just to explain what is meant by similar value decompositions before describing this algorithm, just to give an overview. Now, suppose I have a matrix of dimension, say m cross n, which means I have m rows and n columns. So, each column is of m vectors, right? M dimensional here. Each column is an m dimensional. Now, this can be decomposed as a product of three matrices, and they also satisfy some of the constraints, some of the properties. They are also having certain properties. Let me say. So, three matrices. Let me represent this one U, then say D, then say V. One of the constraint is that they are all orthonormal matrices. So, which means that the columns, if I say U, the columns of U, so let me write it as say U1, U2, these vectors, U3, these are the vectors. So, each are of dimension as you see m, right, and there would be say n such columns. So, this dimension is m cross n, and then D is a diagonal matrix. So, D is a diagonal matrix. So, to use the singular values, I can say this is lambda 1, all diagonal elements are there. These are all zeros. And V is a, I am writing intentionally V1T because these are rows, these are columns. Columns of V is basically, these are columns V1, V2, and this is say n cross n. So, you have n column vectors, of also V of dimension n, and these are the singular values. These diagonal elements are singular values. So, what you can do here, since you are writing in this form, so I can show that actually this A can be represented as the outer product of row and column matrices. So, what is meant by outer product? So, let us try to understand that. So, when we consider two vectors, so let us consider two vectors. Say U is one vector. Now, one of them is row vector. So, let me take V as a row vector. Say V1 to say Vn, and U is a column vector. So, let me rewrite it again. Okay. Now, when we say inner product, we have already defined inner product during transformation. But the inner product constant is that this m and n, they should be equal. Then it is a dot product, and then you can write, as you can see that you can write as, say, b dot u. You can write if m equal to n, right? You assume m equal to n. Then that's the inner product. Or you can also write here u transpose and v also, if I use it as a column vector form, the same vector, that's uniform notation, then I can write it also this. This is my inner product operation, matrix operation. But when you say outer product, then say you notice there what you are doing here, the pre-inner product position. So I should say left operand is a row vector and the right operand is a column vector. So in my column vector notations, we are considering this. But when you are saying outer product, then your left operand is a column vector and your right operand is a row vector. You see, that is the reason, because now inner product will give a scalar value. As you know, dot product will give a scalar value. But if I use outer product, then it will give me a matrix of dimension m cross n. So if it is ui of say length m, say m cross 1, and this is 1 cross n, so you know that it will give me a matrix of dimension m cross n. And you know that this matrix is also of dimension m cross n. So you are getting n such matrices of dimension m cross n whose combinations, whose superposition will give me a weighted superposition. So this is also a kind of linear combination of outer join. We call it also the term outer join of these orthonormal vectors. So that is, let us understand this much. There are algorithms by which for any arbitrary matrix we can get this kind of decompositions. Incidentally, these values could be also 0, right? In some cases these values. So though you have non-zero vectors in u and v, still the contributions to your composition of matrix A would be 0. So we say those kind of matrices as rank deficient matrix, and you know that any non-square matrix is rank deficient. So here the maximum non-zero element would be minimum of m and n. Maximum non-zero element would be minimum of m and n. So it's beautiful theory, and again, some of you, I understand you have gone through this, but once again, please go through and understand what is meant by singular value decomposition, because this is a very fundamental operation which is used in this particular algorithm, which is called K singular value decomposition in the context of dictionary learning. So let me proceed from here. So what we have considered, as you see, that we can start with any code book, and from there we can get its and also the training examples. So examples, and then we have to obtain the sparse representation. So we have to learn these things. And as I mentioned, the Y provides a linear combination of maximum T naught non-zero terms. So that is a sparsity constraint. That is a sparsity constraint. So for which the optimization problem can be stated in this form. Again, you are minimizing, and so in this case you are minimizing a error term, that means approximation error between the product of dictionary and the coefficient matrix and the input data. So in the Frobenius norm that you have used, and subject to that each column vector of y has maximum T naught non-zero element. So this is expressed. This is called norm 0. Like L1 norm, L2 norm, it is L naught norm. L naught norm is simply, it counts number of non-zero elements in a vector, and that is the result. So now what we can do, we will be rewriting this optimization function. The motivation here it is that we will be using a greedy approach, which means I will start with some dictionaries and some representations. As I have also mentioned that suppose you have used k-means clustering, then you can get extreme sparse representation and its corresponding set of and also the corresponding dictionary will be the means of k-means of the cluster centers. That is the dictionary. Those are the atoms, they will form the dictionary. So you start with any particular dictionary and representation. Some good, so initial point is always very important. So you cannot start arbitrarily. There has to be some sparsity in your representations. So there are various ways. So you do k-means clustering, make them as representative. So they are the atoms of your dictionary. Then either you can use extreme sparse representation, or why don't you use the orthogonal matching pursuit and obtain that optimal representations or near optimal representations with respect to that dictionary. So that is a good starting point. Then what we will do, you pick up one of these atoms and see so what is the best way. So if I don't vary others, keep the other atoms fixed, and you find out that what is the effect of this atom. That means what is the approximation error, what is the contributions of this atom in forming the respective data matrix. What is the contribution of this atom in forming the respective data matrix. So that contribution, or I should say that if I don't use this atom, what is the, I should say rather, what is the contributions of the all other atoms which does not, excluding the particular atom which you have chosen for its update, and then find out the error. So that is already you are getting, they are fixed, but the error of approximation that you are going to meet with your chosen atom which needs to be updated. So you get an error matrix. So now you find out, because you know that given that atom, you have to find out those coefficients for each data point with respect to that atom. Now which can be represented in the form of outer join of that atom which is a column vector of D and the row vector of Y. So a row vector corresponding to that column vector, which actually gives you coefficients of that atom for each data points. So since it is outer join, you can perform single value decomposition to get those two components. So let me elaborate it further. So in my representation, as I was telling you, that rows of Y actually provides you the information that for each data, what are the coefficients. So let me explain that also. Say, this is your data matrix x1, x2 to xn. And this is your dictionary matrix D1, D2 to dk. And this is your coefficient matrix. So let me write the column vectors, expand the column vectors. You know that they would be of k dimension and there would be n such column vectors, because for each data point you have a coefficient column vectors. This is n1, n2, nk in my notation. Now you would like to see a coefficients of di for each data point. So from how you get it? You take the ith row. Because when you are expanding, say you consider expansion of x1, what it is? y11 d1 like this plus, and then y1i di, it goes like this. Similarly x2, here it would be y2i di. So if you choose the ith row corresponding to di, it will give you that set of coefficients for each individual data vector. So that is the significance of row. Okay, or here I have used j. So I am just considering the jth row, and it's a transpose operation. It's a kind of notation I am using. Yjt is the jth row of y, and its significance is that, mathematical significance is that those elements are giving coefficients for individual, input data point. As I was telling you that this matrix X can be also represented as outer join of, say, d1 y1 t. See, if I do d1 and take the first row, so d1 and first row, right? So that is what you will be getting. You will get an n cross n or n cross n matrix. Similarly, plus d2 yt2. So this is the way you can get another. No, this is one expansion for individual x1, but the whole matrix, the data matrix can be, let me rewrite once again. So d1 yt1 plus d2 yt2 plus, say, dk tk, which means that if I consider any arbitrary column, say dj, so dj ytj, this product is a contribution towards x. Now this is what we are trying to identify. So if I fix all other atoms and find out their contributions, so what I need to do, what I can do that I can subtract the x from x. I can subtract the, because they are not exactly equal. So I should write here. Otherwise, you might have thought that just subtracting this from x will give me the contributions from others. That is not, because it's not exact. It's an approximation. So what you have to do, you have to subtract, say, every contributions yt I equal to 1 to k, but I not equal to j. This is the contribution. What you will, this is the, I should say, not residual part, and this is the contribution of the atoms excluding j, and this is the residual part. Now this residual part you are trying to match with dj ytj. So you have to find out that dj and that ytj whose outer join should be equal to this residual or a closed. So one of the best way you can do is that, exactly you can do that, because if I do the singular value decomposition, as you can see that if this is my matrix, I will make a singular value decomposition. Say u d v. Here this d is not the dictionary. So let me use a separate symbol for the diagonal matrix. Say US V transpose. Okay, this is a diagonal, and so U gives me one of the column vector and V transpose gives me the row vector in my notation. So it is fine. So what I will do, since S is my singular values, and the best approximation would be always with the largest singular value, and the singular value decomposition you can rearrange the columns of U and V in such a way that the largest singular value occur at the first diagonal element. So you take the first column vector with respect to the largest singular value. So if it is rearranging only the first index, and that is basically di, and the rest thing, that means the respective row or the first column vector of V multiplied by the singular value, corresponding singular value, will give me YTI. Is it exact? So you know that your approximation wise it is good. Problem is that sparsity constraint may not be satisfied, because after decomposition these matrices may not, and mostly they will not remain sparse. So you require some more tricks to do that. That means you have a sparse vector already. So you know that your YJT is quite sparse because you started with kind of near optimal representations with respect to direct dictionary. So there are quite a few zero elements that is expected. So at least those zero elements should still remain zero. If you can ensure, and after that you try to approximate, then it would be good. So for that, you may not try to reduce the whole error in one shot. A partial error, you find out only that part of contributions, or that part of contributions of samples. So now again it depends upon which sample. So for those non-zero coefficients of the kth atom or jth atom, you know that there are certain samples where these coefficients are non-zero. I mean, for constructing them, the jth atom is playing a role. So only restrict yourselves reconstruction of those samples. So your approximation error will be related to the reconstruction or to the composition or to the formation of only those samples. So you take a subset of these column vectors, which means you have a reduced size of your input data vector. Similarly, since you are taking subset of these column vectors, similarly from the Y coefficient matrix also you need to take only those coefficient vectors corresponding to that subset. So your Y also becomes reduced. Because for rest of the column vectors you are still enforcing the component, there is no contributions from your jth atom. So result is known, this should be 0. So now you modify, now you recompute this error with respect to those reduced input data matrix and also reduced coefficient matrix. So define similarly the error of approximation by other atoms excluding the jth atom, because we are considering jth atom is my reference. This is my reference here, for we are updating the jth atom. So find out that what is the residual, then you get an decomposition, singular value decomposition, get an outer joint which will try to match that residual. Exactly that is possible. It will be, you just make a singular value decompositions and get those, remove that residual part, and then update the respective atom dj and also the respective row of y, jth row, only the non-zero positions. Zeros are remaining intact. And you perform these operations iteratively. So for k atoms, you do it k times in one iteration. You get always some representations which is sparse. So after some times, after some iterations, you will find that there is no more changes, no more improvement. It gives you back the same result, almost same result, near almost similar results. Or these residual errors are coming zero, which means you cannot proceed further. So you stop updating then. So this is a algorithm. So once again, let me give you the summarized form of description. So as I was telling you, this is the representation that this error of approximation can be expanded in this form. Say sum of outer join of atom and the row vector of the coefficient matrix Y. So respective atom with respective row vector, you should note here. So as I was telling you, this is the expression where here I have considered kth atom. So you are considering contributions from all other atoms excluding this kth atom, and then find out what is the residue, what is the residual error. And that residual error you are trying to minimize with your updated atom and its coefficient corresponding rows of the coefficient matrix. So this is what you are going to do. So let me represent it as a matrix EK. It's of same dimension. You can see X is of dimension, say n cross n. These are all dimension of n cross n. Individual matrices all are dimension of n cross n. So EK also is of dimension of n cross n. This is also dimension of n cross n. So every operation is valid. So you perform singular value decomposition. Now this is I am saying that without any reduction. So this is just for your understanding that you perform the singular value decomposition. As I have mentioned, you get these matrices and take the columns of U and V for maximum singular value. So D1. So it is generic, but you can rearrange and you can make this element its maximum. Then you take the first column of U and first column of V. I am saying first column of V, which means first row of V transpose matrix. Okay. So this is what for D11. So as I was mentioning that this column vector may not be sparse. So for enforcing sparsity, you choose only samples from X which have a non-zero component along decay. And then you reduce this matrix. Reduced matrix is EKR, which means that you are choosing only those samples. Say these are the column vectors you have, and suppose your coefficient matrix Y at kth row, because I am with respect to decay, it has only some non-zero element, say 1, say 2, like this, only say 2 non-zero element, rest is 0. Say this position is I and this position is J, which means that you will be taking from this, you will be reducing it to a input data point only with these two vectors. So its dimension in this case will be n cross 2. Similarly, your coefficient matrix, you will be considering only this 2. So YR, so this is your XR, this is your YR, YR should be also YI and yj. So using this, now you apply the same operations. From there you obtain EKR and this. So update this and repeat for all dj's and obtain updated d and y, and repeat till it is converged. Okay, so performing SBT k times for k atoms in each iteration. I have explained that also. So just once again, this is summarized from algorithm. You have forming an initial dictionary, obtain an initial sparse representation, and then you iterate for every atom greedily. And you can use k-means clustering, you can use orthogonal matching pursuit algorithm. There are various applications of these sparse representations, say compression, denoising, de-blurring, super resolution, where you can map the learned dictionaries, in painting, so you can use them for in paint the region which is masked. So just let me conclude this topic. We are coming to the end of this lecture. So sparse representation we have discussed, some pursuit algorithms like matching pursuit, orthogonal matching pursuit, basis pursuit algorithm, though we have not elaborated, we just defined the problem statements. Then dictionary learning and sparse representation also we have discussed. Particularly we have discussed this algorithm, k singular value decomposition. So with this let me stop here, and this is the conclusion of this particular topic. We will start a new topic in the next lecture. Thank you very much for your listening.